moment of inertia of a solid sphere. So as I said, whenever you say moment of inertia, you have to also say through which axis. So this is about an axis through the diameter of the sphere. So since it is a sphere, it will always all the diameters will pass through the center of mass, which will be the center of the sphere. Okay, so that's the center of mass, and your axis of rotation is the diameter, like this. So we will take an horizontal line here. So the rotation is happening, let's say this way. So your sphere is rotating this way out of the plane, spinning that axis. So you have to find the moment of inertia of the sphere. So for that, what we do is that we will consider a slice on the sphere. Okay, so we consider a slice. You're going to make a thin slice like this. Okay, and this slice will be a disc. You will get a disc if you slice like this on a sphere, on a solid sphere. And the radius of the disc, I will call that as y. The radius will be from this point to this point. That will be the radius of the disc. That I will call as y. And the thickness of the disc, this thickness I will call as dx. Okay, the thickness of the disc, which is a small thin disc. And the mass of the disc I can call that as dm. dm is the mass of the disc. Okay, and I consider the disc, I can consider it anywhere on the sphere. I can slice it anywhere on the sphere. Let's say that I have sliced it at a distance of x. So this distance between the center of mass and the disc is x. And from the figure, I can connect these 2 points, and that will be the radius of the sphere. Capital R is the radius of the sphere. And let's say that the mass of the sphere is capital M. So what you have here is mass of the sphere is capital M, and volume of the sphere is 4 by 3 pi r cube, where r is the radius of the sphere, and mass per unit volume. Mass per unit volume will be the total mass divided by the total volume. And you can simplify this. Just take this 3 to the numerator. That will become 3m by 4 pi r cube, which is nothing but it's called density. Mass per unit volume is called density. Usually the symbol is rho. Okay, symbol is rho. And you have to find this dm. Your moment of inertia is actually dm r square. In fact, mr square, integral dm r square. So you have to find this dm, mass of the disk, mass of the thin disk. I will call that as dm. I have to find this dm. How do you find this dm? That dm will be the density times, so let me write it, density times the volume of the disk, volume of the disk. So what is the density? Density is rho, and the volume, volume of the disk. So how do you find the volume of the disk? So you see the disk can be drawn like this. You can just imagine a disk is nothing but a short cylinder. Okay. A very short cylinder is actually dx, and you know how to find the volume of a cylinder. It is pi r square h, where r is the radius of your cylinder. Here the radius of the cylinder is y, so it will be pi y squared h. H is actually dx. The height of the cylinder is dx. So that is your dm. Okay, that's your dm. So you can substitute for density. Density is 3m by 4 pi r cube times pi y squared dx, and you can cancel the pi here and you get this 3m by 4r cube y squared dx. That's your dm. What is it? That's the mass of the disk. Okay, so this disk, when it is spinning, how is it spinning? It is spinning. So let me draw the disk once again. So let me draw it this way. So that's, so let's say that this is your disk, and it's spinning in this axis. Okay, the axis is this way. It's going through it. Okay, so that's how this is spinning. Okay, this one, it's spinning this way. So this is actually a inertia of the disk rotating about an axis, passing through the center of mass and perpendicular to the disk. This one we derived it a couple of classes ago, and that will be equal to the mass of the disk. So this is equal to mass of the disk multiplied by the radius of the disk squared, actually squared, divided by 2. That will be the moment of inertia of the disk, which is rotating this way. And in our case, the disk is also doing the same thing. This slice is doing the same thing, and the radius is y and the mass is dm. So your formula for the moment of inertia of that our disk is actually dm y square by 2. So this is the moment of inertia of a single disk. Moment of inertia of the disk. Okay, we are not interested in the moment of inertia of the disk. We are interested in the moment of inertia of the sphere. But the sphere is made up of a large number of disks of various radii. Okay, you change the radius of the disk, starting from a very small disk to just keep on increasing the radius. That will give you a hemisphere, and do the opposite. Start from a bigger one and go to a small one. That will give you the other hemisphere. So which gives you a complete sphere. So this is for just one disk. Let's substitute for dm, and we have to do it for all the disks. Y will be changing. So let me substitute for dm. Dm is obtained here. So number these equations. Let's say I will call this as equation 1, and this as equation. Substitute 1 and 2. What do you get here? You get, this is 3m by r cube, 4r cube, y square dx in y square by 2, and that gives you 3m by 8r cube y power 4 dx. This is the moment of inertia of one disk. You have to now integrate it over the variable x. So the integration variable will be x. You have to integrate it over that with the limits. So the limits will be, since you measure the distance from the center of mass, we usually take that to be 0. And this extreme will be minus r, and this extreme will be plus r. So your integration, your x will vary from minus r to plus r. That will be your integration limits. And since y is also a variable, x is also a variable, you have to replace your y in terms of x. For that, again, we use this triangle here. You can name this triangle if at all you want. OAB. Let's say OAB is a triangle, right triangle. So from the right triangle OAB, let's say, let me write it here, from triangle OAB, we can write r square is equal to x square plus y square. Otherwise, your y square will be equal to r square minus x square. Okay, so that's your from the triangle Pythagoras theorem, x square plus y square equal to r square. So replace your y power 4 from this one, so that gives you so let's integrate it. So the moment of inertia of the sphere, moment of inertia of the solid sphere, let's call that as I is equal to integral 3m by 8r cube into let me write it in terms of y power 4 itself. Then I will do the substitution. Y power 4 dx. Did I miss something? No. 3m by 8r cube y power 4 dx. That's it. So this is the moment of inertia of the sphere rotating through an axis. About its diameter. About the diameter. So with the limits minus r to plus r. So let's substitute for y square. So let's take out this constants. So these are constants which are not affected by the integration. And y power 4 will become r square minus x square whole square. Because y square is r square minus x square. This is y square whole square. So this is r square minus x square whole square dx. Now you have to do this integration, which we actually did yesterday. You have to expand that bracket, and then integrating will be easier. So expand this. This becomes r power 4. This is r power 4 plus x power 4 minus 2r square x square. The whole thing is integrated with respect to dx. This is equal to 3m by 8r cube. And now let's integrate this one. So r power 4 dx will be r power 4x plus x power 4 dx will be x power 5 by 5, and this will be 2r square x cube by 3. That will be the integration with the limits minus r to plus r. This now you have to substitute the limits. You have to substitute the upper limit first, then minus of the lower limit. So let's do it carefully here. So substitute the upper limit. So r x will be replaced by capital R, so that will become r power 5, and plus x will be again replaced by capital R, that will become r power 5 by 5 minus 2 by 3 r square. Here x cube is now replaced by r, so that will become r cube, and r square you have, so that becomes r power 5. This is your upper limit minus of your lower limit. So lower limit, let's put a bracket here because the minus is common for all the terms. So this is minus r. You have to substitute for x as minus r. So that will become minus r power 5. And again for x you have to substitute for as minus r. And this is minus r power 5. That will become a minus r power 5 by 5. And you have x cube. That will become minus r cube. Already you have a minus sign, so that will become 2 by 3 plus r power 5. Okay, that's it. Okay, now r power 5 is common. You can just take it out. So this becomes 3m by 8r cube into r power 5. This becomes 1 plus 1 by 5 minus 2 by 3. and you can just take this negative sign inside. That becomes plus 1 plus 1 by 5 minus 2 by 3, and you have this r cube and this r power 5. You can cancel it. This becomes 3 by 8 mr square, and you have 1 plus 1, that gives you 2. 1 by 5 plus 1 by 5 gives you 2 by 5, and minus 2 by 3 minus 2 by 3 will give you minus 4 by 3. Now take an LCM here. 3 by 8 mr square. Now if you take an LCM will be 15. That will be 5 times. So this will be 30 plus 6 minus this will be 5, 20. So what do you get? 36 minus 20 is 16. So you get 16 by 15, and you can cancel this 2 times, and you can cancel this 5 times. So you get 2 by 5 mr square. So that will be your I, the moment of inertia of a solid sphere rotating about its diameter. Okay, that's the end of this one.